and we're here to talk about using different ideas from mathematics, particularly from set theory, in order to untangle the problems of time travel and time paradoxes. Now, who am I and why should you care about what I have to say? My name is Dr. Edmund Schlussel. I have a PhD in theoretical astrophysics. I specialize in gravitation and cosmology, but that is basically applications of Einstein's theory of general relativity. So I've worked extensively with curves in space-time, with different dimensional spaces and things like that. I'm also a teacher of mathematics. I teach at the International School of Helsinki, grades 9 through 12. And I'm an author. And some of the ideas that I've discussed in this talk are things that have come up in my stories. That link there is to my blog. So a couple of years ago, I saw a talk at a Fantasticon at a Fantastica in Stockholm that was purporting to put forward a grammar, a way of handling linguistically these different kinds of timelines, and the presenter proposed a way of resolving time paradoxes that was very subjective, but also very artificial, in my opinion. And not to trash what they were saying, I actually have forgotten who it was, so I can't challenge them directly on it. Um, but it occurred to me that a lot of the things that we see as paradoxes as a result of our own experiences with time being more or less linear um, are not so much paradoxes as much as they are uh, things that come up from the structures of the way that we think about time as being a one-dimensional process with a hierarchy of reality and possibility. Um, I'm not going to comment on all the world's languages or invoke the Sapir-Whorf hypothesis or anything, but in most Indo-European languages, you have a past and a present tense and often a future tense. It's usually an innovation, but a lot of languages have innovated that. And an idea of time being linear from past to present to future, and then the implication of some alternative timeline, would, could, should, some conditional. Um, and this is fine. It fits with our experience of time in an everyday situation. Now, of course, Douglas Adams started playing around with this idea and started in one of his books. He listed some possible verb tenses or some ways to conjugate verbs in order to indicate things with time travel and changes of timeline in a purely flippant way. But that's the earliest example I know of trying to accommodate these things into our more conventional experience. And the way that we experience time is like the frames of a movie, a sequence of events, one following the other, by strict relationship of cause and effect. I'm being pedantic about this because this is something that we'll be referring back to. Now, for purposes of simplification, I'm going to treat time in this talk as being these ticks of a clock or these frames of a film rather than something continuous. I am hand waving a bit there when I do that. Uh, but it is much easier than dealing with the multiple kinds of infinities that we would run into if we were talking about time as continuous. Plus, we would run across problems that are as yet unresolved regarding quantization and regarding the idea of a smallest possible, smallest measurable unit of time. So this is what we want to try to get back to if we're resolving time paradoxes. We have this everyday experience. Then time travel comes along, and the possibilities of time travel mess with that experience by implying that time might not be a linear sequence of events, that experience might not have this simple sequence of cause and effect. We want to try to recover that. We're used to the idea of numbers being orderable. One of the first concepts we encounter before we even really build the ideas of addition or multiplication is the idea of counting. And counting happens in a strict linear sequence where you either have less than a certain number, the same number, or more than a certain number of something. And how for any two numbers in our ordinary experience, you can compare these numbers. And this is true for whole numbers, but it's also true for fractions or for the irrational numbers or for the negative numbers. We can look at any two numbers and say one's bigger than the other one, or they're the same. And those are the only options. And this is what's called well ordering. It means that we can take any numbers we run into and put them in a sequence from smallest to biggest. Now, I am simplifying a bit, and I want to motivate that a bit more. Part of the problem, and something that I think that goes unrecognized when people try to make time travel stories, is that while the universe is not necessarily this strict linear sequence of events, any event that happens is strongly dependent on its context. The universe is what we call chaotic. There's lots of ways to define chaos and lots of different perspectives you can come at the idea from. But for our purposes, what we care about with chaos is that if you want to know what happens in the next second, you need to know absolutely perfectly what happened in the previous second. You can't miss any details because the impact of those tiny, tiny changes are much, much bigger than the scale of those changes. The other thing, and this is where we do have to invoke quantum mechanics, is that the universe is probabilistic rather than deterministic, as far as we can tell. In other words, when we look at, say, the decaying of an atom or the breakup of a molecule, we are looking at a process where the laws of probability govern what happens, where we cannot say, purely by looking at all the pieces of that atomic nucleus, what is going to happen. We seem to have a pure probabilistic physical process going on at the quantum level. And because anything that you build up out of those smaller pieces, out of atoms, will inherit the properties of those individual particles. That means that in a macro sense, the universe is chaotic. We could ignore it on some scales, but in a fundamental way, the universe is unpredictable without perfect knowledge. And even with perfect knowledge, we can still only talk about likelihood of outcomes. Meanwhile, we have this question of putting events in order. Now, one of the things that comes up in special relativity is this idea that events don't, that the idea of simultaneity is no longer strict. Let's say that you have three people, or two people and a lamp, and the two people are some distance from that lamp. The lamp goes on. Both the people make a note on their watches when they see the lamp turn on. In a situation where you can treat the speed of light as infinite, then the people see the lamp turn on at the same time. But when the speed of light is finite, as we know it is in the real universe, then who sees what happening in what order depends on their relationship to the event. And then, of course, they're limited in how they communicate that information to each other. So we can't have strict ordering events in special relativity. We have this same issue in mathematics. That horizontal line on the graph there is the numbers that we're used to, the so-called real numbers, the counting numbers, the numbers that you might have in your bank account, positive, negative, zero. But pretty soon, when you're working with numbers, you run into the necessity of defining a second category of numbers, of generalizing the real numbers to the complex numbers, really giving the numbers another dimension. And this is something that you would do, for example, to solve a quadratic equation in the most general case. It will come up in the theory of electrical circuits, or when we're talking about the relationship between exponential growth and waves. You'll run into this idea of a complex number. I cannot show you 2 plus 3i apples any more than I can show you negative 2 apples. But logically, for our mathematics to be consistent in our everyday sense, these complex numbers have to be there in the background. And they come up in all kinds of places. They come up in relativity, in quantum mechanics. They seem to be under the table of the universe in a certain sense. So this idea of simultaneity is an issue because we really need to be able to say, when we said that we're putting we're putting numbers in order, and we're saying the numbers are either bigger than one is bigger than the other, or they're the same. This idea of simultaneity plays that same kind of role. Either one event happens after another, or they happen at the same time, and those are the only possibilities in linear time. Now I want to call your attention, this is an XKCD comic, by the way. I want to call your attention to the flow chart in the bottom right of the movie Primer. I don't know if you've seen that film. Primer is a film that relies heavily on time travel, alternate timelines, and paradoxes of information. And what Randall Munroe's tried to draw there is a flow chart of the timelines in that film. It's a very difficult film to follow. You need to watch it a couple of times to really get what's going on. So how do we start to resolve this? Well, there's two big schools of thought in quantum mechanics. The one that you run into most of the time is the so-called Copenhagen interpretation. And that is the one that I described earlier, where you look at an atom and there's a 50% chance that that atom will decay in the next minute. And you treat that decay, whether it happens or not, you treat that as a purely probabilistic process. There is some wave describing the atom that can exist in either of two states. Somehow the universe picks one of those states, and you live with the universe that you're given after that. But there is another way of looking at the different outcomes in a quantum mechanical system, and that is the so-called many worlds interpretation. Many worlds, the idea is that whenever you have some quantum decision, the universe splits in a certain sense and follows both routes. Your own consciousness only follows one. There's some copy of you in the other universe that's experiencing the other outcome. So if you follow any of these lines along, that is one person's particular world line, their particular timeline. But you have, in theory, although they're completely inaccessible, all these different universes, all these different outcomes every time there's a quantum decision. Now, when we talk about time travel, then, we're talking about going back along one of these world lines. And then if we do anything that changes the outcome, including, I think, our own presence in the past, we follow a different timeline, a different world line. So when we talk about time travel and traveling to parallel universes, through the lens of the many worlds theory, those are kind of the same thing. Okay, so we've got this weird splitting process going on. And that seems to be paradoxical. Because all of this is centered in the theory of relativity and the theory of quantum mechanics, and something that is very, very strictly detailed in both of them is the idea of conservation of certain quantities. It's actually more fundamental than the flow of time itself, the idea that you cannot create momentum out of nothing, you cannot create matter out of nothing. And yet here we are, we've created an entire new universe's worth of matter every time we have a quantum decision. We duplicate everything in the universe. It's a horrible, grotesque violation of conservation of matter and energy, isn't it? Well, not really. There is a loophole. This is where things start to get kind of weird. Let's say that you have a sphere. It's a sphere. It's a mathematically perfect object made up of an infinite number of points. In 1924, Stefan Banach and Alfred-Tarski showed that there's a way to take some bounded set. A sphere is a good example to start with, but it could be any shape. It could be a rubber duck, could be a cube, could be anything. And decompose it. You pull apart the pieces and you reassemble them. That seems straightforward enough so far. And you get two spheres that have, and this is where it gets really weird, the same number of points in each one. You've taken an infinite set and you've turned it into two infinite sets. In one way, this seems almost obvious, because if you take half the things out of infinity, you're still left with infinity. There is a lot of detail here that I am glossing over. But at the same time, there's a real problem with this, because this is a mathematical theorem, but if you applied it to something real, so you had a chocolate bar, you would be able to take a 500-gram chocolate bar and create two 500-gram chocolate bars out of nothing, simply by carrying out an operation where you pick out certain points in the original chocolate bar and sort those points into either the first new chocolate bar or the second one. Somehow in that process, you created something out of nothing. Now, I grant you that this may sound ridiculous, but it's a consequence of something else. And that something else is something that doesn't sound ridiculous at all when you actually start using it. That something is what's called the axiom of choice. In the Banach-Tarski paradox, you had to look at every single point in an infinite set and decide, does this point go in chocolate bar number 1 or in chocolate bar number 2? If these points all came in a nice, neat order, this would not necessarily be a huge problem. But because we don't have a way to put three-dimensional objects in order, we're in the situation that we have to make an arbitrary choice to start this process of dividing up the set, and we have to make an infinite number of arbitrary choices to complete the process of dividing up the set. Is that a valid way to build a set, by making an infinite number of choices? The axiom of choice says yes. The axiom of choice is something that you cannot prove. It is something you have to either accept or reject. And it is an idea about how infinite sets can be formed, about whether or not it's okay to make choice after choice after choice. You can have a rule for it. That's fine. It doesn't have to be random. And say that the sets you get out of it are validly defined. Now, as we just saw with the Banach-Tarski paradox, it can produce weird results. But if we reject the axiom of choice, the results we get are weirder. Like, let's say I give you a list of a few numbers and tell you the rule, put these numbers in random order. Sounds easy, right? Now let's say I ask you to imagine doing that to all the natural numbers. Take the entire set of natural numbers and randomize them, starting from 1 and going all the way to the largest number you can imagine, and a bigger number than that. We can picture doing that. But actually doing that is not something that we can do on paper easily, because there's an infinite number of numbers to choose from. If we reject the axiom of choice, we say, no, we can never actually do that. But if we take the axiom of choice, we say that in principle, we accept that in principle, yeah, we can randomize the entire number line. And if we can do that, well, that's the same as saying we can randomize all the numbers between 0 and 1. So that seems like we're on solid footing there. By the way, thinking back to quantum mechanics models, to the Copenhagen interpretation versus the many worlds interpretation, if we're going with the Copenhagen interpretation suggests that the universe is somehow picking between different outcomes of these quantum decisions in a way that follows some rule that is arbitrary or not necessarily clear to us. So, for the way I see it, whether you're looking at the many worlds model or the Copenhagen interpretation, the axiom of choice has to be in there one way or another. But the big outcome of all this is, if we accept the axiom of choice, we've kind of already solved the problem we started with. Because the problem we started with was we have all these events in space and time, and no particular order to put them in. The axiom of choice says, well, we can make an infinite number of choices about that set of events. We can take the frames of the movie and take the frames of every possible movie and put them in whatever order we like, and that's a valid choice. That's kind of a cop-out, but it is, again, in principle, a way to solve the problem of ordering events with time travel by saying, well, whatever order we choose is a valid order. I'm going to do something a bit better than that now. By the way, before I move on, I want to just note the semiotics of this progression. We started out with the idea of time being an absolute imposed from without, something that we couldn't do anything about. We looked at that in the real world and we found contradictions stemming from relativity, stemming from things that actually have to be true for the universe to work consistently. And that pushed us toward the idea that time is an individual phenomenon, which was not very satisfactory, the idea that we can throw the frames of the movie in whatever order and say that's valid, it's my choice. But as we go, I'm going to show you a way that we can rebuild the idea of time as a construct that we can work on together by social consensus. A lot of you are familiar with the word hologram or the idea of holographics. A hologram is, well, in the mundane sense, it is the little on your credit card or your debit card that looks like a 3D image, but it's printed on a 2D piece of plastic. But when I talk about holographics in a more general sense, what it means is it's a way of making a map from a three-dimensional object onto a two-dimensional surface while keeping all the information. It's a way of taking many dimensions and mapping them on to fewer dimensions. I'm going to be careful here and say I'm not claiming the universe is a simulation. I'm not claiming that the universe is all some computer code or something. A lot of the less responsible science journalists go that direction with ideas like this. It is a possible conclusion, but there's no evidence for it. I'm not going to assert it out of the blue. Instead, what we're going to do with holographics is this. Let's say that we have a ball, a sphere, and we want to encode the information in that sphere onto a two-dimensional surface. Well, what is a hologram actually doing when we think of our three-dimensional images on two-dimensional plastic? Think about looking out a window. The window's a flat surface. As you change where you are in relation to the window, the image that you see outside the window changes a bit because of your perspective. The light from whatever vista you have, from whatever you're looking at, is passing through the window. That particular vista is associated with your particular perspective relative to the window. A hologram is recording all the different angles of that vista into the window itself. So each speck of the glass contains the information of what does the window look like from this angle, from this angle, from this angle, from this angle, from this angle. Now, if you were at my talk Worldcon 77 about the quaternions, we talked a little bit about these more general kinds of numbers, 4-dimensional numbers, 8-dimensional numbers, 16-dimensional numbers. But they always have a real part on them. So these higher orders of numbers, I don't want to get too deeply into this part, but these higher orders of numbers kind of do exactly what we want, because we can put the real parts of all these numbers in an order, and each of these numbers encodes along with it a vector. Where am I going with this? Well, we have our ball, and that ball has information in it. If we're looking at that ball from the outside from every possible angle, the light from inside the ball is passing through the surface. We're going to peel off the surface of that ball and bring with us a recording of what the inside of the ball looks from every possible angle as the light inside it passes through the surface. And that will give us a two-dimensional surface of a three-dimensional object. But then we can take that peel and we can cut it in a spiral. And if we make that spiral infinitely thin, which we're allowed to do because we have just a set of points, and points have no width and no breadth, we end up with a string, a spiral around the outside of the ball that carries all the information that was inside the ball. We've mapped a three-dimensional object to a two-dimensional object to a one-dimensional object. But what we've done when we've done this is we've taken all the information in that three-dimensional object and mapped it onto a one-dimensional surface, in other words, onto a line, something that has a beginning and an end and an order to it. There's some arbitrariness in how we do this, yeah, but we can always map between different ways of peeling this orange. We have a universal calendar. We have a way of ordering events for one particular universe. We have a way of putting space in order. So our next step is going to be to take those different strings, those different peels, and connect them end to end. And that gives us the events in every possible universe in order, with a beginning and an end. All the things that could happen, all the possible timelines, are now in a strict linear sequence. We don't have to experience them in the order that they're on the tape. There is, though, some hyperdimensional, hyperspace, hypertime perspective where all these events are in some kind of order. That is a well-ordering on the events in the universe. This is also, if you think about it a bit of a different way, we have every event that could ever happen laid out in a linear way, each event implying the next one. Remember we were talking about this at the beginning, how if we have perfect knowledge of a moment, we can predict the next moment. That's instructions to get from one point on this string, on this list, on this tape, to another one. And what's that? Well, again, I want to make sure that I'm saying what I'm actually saying. I don't want you to get the wrong impression here. I am not saying the universe is a computer simulation. What I am saying, though, is that if we have discrete events and a set of instructions to go between them, we have something that is basically the memory tape of a Turing machine. How can I get away with the claim that it is a Turing machine specifically, or that it maps to a Turing machine? Well, you can build Turing machines in the universe, which means that the universe is Turing complete. And if that's true in every universe, that means we can treat this entire tape as a Turing machine tape. This has given us what we're trying to get. We have all the events in history laid out in order end to end. We have not gotten rid of arbitrariness. But whatever arbitrary choice we make about ordering, there is still a set of rules to help us go from one point to another. We have not broken down into chaos. We still have cause and effect. We've generalized the idea, but we are still talking about something which could, in principle, be computed. So that's the end of our journey for today. Here are some places where you can buy some of the stuff that I'm writing about. In this story in particular, down here in the bottom right corner, I actually deal with this problem in considerable detail. And I talk about what would the experience of time and order be like to beings that exist beyond time and space, and who can deal with infinity. This has gone a bit shorter than I expected because of the one-way nature of this recording, so I'm looking forward to your questions in the live session. Thank you very much, and I'm going to assume that you've been a good audience, and have a good day.